Hello, this is Dr. Maxwell, and in this video I am going to work problem 5 from homework 16, where we're asked to graph the rational function y equals x over x squared minus 49. So these first few questions that I have here we can answer without looking at the derivative, but we do need to factor the denominator. Since that's the difference of two squares, that is easy to do. Okay, so now we can see that the domain is all real numbers except whatever makes the denominator 0, and that would be positive 7 or negative 7. We also can see that we have two vertical asymptotes, one at negative 7 and one at 7. The horizontal asymptote, remember we find that by looking at the limit as x goes to positive and negative infinity of this function. We get the same result whether we're looking towards positive or negative infinity. If you work this out, this limit equals 0. And remember how we interpret this. This is a horizontal asymptote. Okay, so we already know a lot. The y-intercept is going to be 0. How do I know that? Well, to find this, you let x equal 0. Y would equal 0 over negative 49, which is 0. So we have a y-intercept of 0, 0. And I'm going to say 0 one more time because we also want to see if this graph crosses the x-axis. And to do that, you set it equal to 0. But, okay, so let's just do that. This will equal 0 when x equals 0. So our y-intercept is our 0. Now symmetry, I'm going to test for odd. How do I know to do that? Well, if you look at this function, I can tell that it's not going to be even because this x up here is not squared. And I might not be 100% sure. I might not remember this is going to be an odd function. So I'm going to test for odd. And how do I do that? Basically, we plug in negative x, and if that equals the negative of f of x, if this is true, then we have an odd function. So let's do that test. So I will write f of x equals x over x squared minus 49. And now I'll test for odd symmetry because this will save us some work if it does have symmetry. Okay, so f of negative x looks like this. Everywhere you see x, plug in negative x. And then simplify. So f of negative x looks like negative x over this negative here gets canceled. Well, we multiply it by itself, so I hope you see what I mean. Now, I'm not sure, is that negative f of x? How do we see this? Well, the way I see it is to bring this minus sign out front. This is f of x, right? So, yes, this does equal negative of f of x. So our function, we'll call it f. What kind of symmetry is this? Origin symmetry. So origin symmetry, if you remember, example, this is not our function, of course. Y equals x cubed. It has origin symmetry. Any point up here, which I would call x, y, has an evil twin down here, negative x, negative y. Okay, so now we're going to look at the derivative. I might as well just call this f of x and remember we will be using the quotient rule. Which I know you know by now. Okay, so let's see what this derivative looks like. Draw my great big divides bar, put the denominator down here, and square it. The derivative of the numerator is just 1 times the denominator minus the derivative of the denominator, which is just 2x, times the numerator. Okay, that's the first step. Now we need to simplify, which means get rid of the parentheses and combine any like terms. Okay, so what our derivative looks like, I can combine these two. In the numerator, I have negative x squared minus 49. And in the denominator, I have x squared minus 49 squared. It might be very tempting to try to simplify this, but those are not the same thing. And the way that I see it is by writing the derivative like this. My denominator is unchanged. I'm going to factor out a negative 1 in the numerator. So now I can see, oh, yeah, those are very different things. There's no cancellation. I also, of course, we want to find critical points. So if we set this equal to 0, which we will do on the next page, so I want to see if this can ever equal 0, well, remember, zeros only come from the numerator. So the question we're asking is, can this well, let's back up. This here, this is just a constant out in front, minus 1. So what we really want to know is, can this equal 0? Well, look what happens if you try to solve this. There is no real number that you can square and get a negative result. So the derivative has no zeros. Now, the other kind of critical point comes from when the derivative does not exist. Remember, that's what we're looking for, critical points. Well, this derivative does not exist at f prime of 7, and the derivative does not exist at negative 7. However, these are not in the domain of the function. Now, I'm doing a lot more detail than is required to answer this question on Canvas, but I think this is all a good review. So that's why I'm working this problem like this. So bottom line, there are no critical points. Isn't that interesting? What does that mean? Well, we will not have a max, and we will not have a min. What about our behavior? Increasing, decreasing. Well, let's talk about that on the next page. Okay, this derivative is always negative. You can plug any number you want to in that derivative where it's defined, not 7 or negative 7, and the result is going to be negative. How do I see that so easily? Well, look at the numerator. This expression inside the parentheses, this is positive, and we're always multiplying by this other factor that is negative. So that is negative. Then look at your denominator. Anywhere this is defined, this is positive. So overall, I have my derivative looks like a negative over a positive, which tells me it's always negative. So my original function is decreasing everywhere. Well, not quite everywhere. Let's be a little more precise. On negative infinity to negative 7, negative 7 to 7, and 7 to infinity. Because remember the domain, we had to exclude those two numbers. So this will be helpful when we come to graphing it. Okay, so let's see what we know so far. All right, so we know the function is always decreasing. It has a horizontal asymptote, y equals 0, x-axis, remember. Has two vertical asymptotes, and we know where the 0 is. What we need to know is behavior at the vertical asymptotes. So remember, to do this, I like to just draw a little picture, and this can represent my vertical asymptotes at x equals 7 and x equals -7. Now, because of symmetry, we only have to test one of the vertical asymptotes. So let's test this one. What is the limit as x approaches 7 from the left of our function? Well, remember how you do that. You're going to test a point in here. So maybe I will test 6. I will put 6 in the original function, and so maybe I just will look at that over here. If you put 6 into this expression, the numerator is positive, but the denominator is negative. Remember what that tells me? That my behavior at this vertical asymptote will be going down to -infinity. Now I already know that this also comes up and has a 0 at 0. And because it has origin symmetry, odd, we're going to do the opposite thing on the other side. So I don't have to test going towards -7. I only need to test going towards 7 from the other direction. All right, let's do that here. And maybe I'll test 8. If I put 8 in here, remember this was for 6, I would get positive over positive, wouldn't I? What does that mean? As I approach this asymptote, let's get rid of that arrow, my behavior is like this. So that means down here at -7, I do the opposite thing. I go down like that. So we already know that's what the graph should look like. It's not a very good picture, but I even know the end behavior because of my horizontal asymptote. Remember? Right here. So the piece of the graph here is just going to approach y equals 0, get closer and closer to the x-axis. And here it's doing the same. It's never going to cross again because there's not another 0. That's it. We're done. But maybe we want to verify that it is always decreasing. So remember, when you look at this question, you're always traveling from left to right and asking yourself what's happening to the function or the graph as you go from left to right. So as we're like riding along on this piece of the graph, as we go from left to right, we're always going downhill. Then we have to jump over the asymptote. We start way up here, but again, as we go left from right, we're always going downhill. That means decreasing. Downhill. and then we jump over the last asymptote. We start way up here, but as we move in the direction to the right, we are going downhill. So yes, this checks out too. So let's just take a quick look at the Desmos graph. All right, here is our graph, and it looks sort of like what I drew. It's kind of hard to see maybe, but you can see I've got our vertical asymptotes in orange, and here's my zero. We have no max, we have no min, we're always decreasing. The end. Well, almost the end. I'll tell you the easy way to answer this question on Canvas. You get to choose from the graphs. So if you know that we have the vertical asymptotes that we do and we have the horizontal asymptote that we have, I think there was only one choice that gave you the correct answer. So this question for me, I didn't have to do any work. I just looked for the right asymptotes and chose the right answer. But that said, everything we did is a good review of skills that you need in this course. So now it's the end. Bye.